Dom DeLuise used to say, hold the applause until the end. You never know. One nice thing I have about reading this is there are no questions after this. I'm not a Galileo expert. In fact, somebody asked me before, who was Galileo? I said, he makes pizzas over on 42nd Street. Anyway, Galileo played a major role in the development of methodology of modern science. And he did so not all of a piece in the abstract, but by actively pursuing knowledge of the physical world over a lifetime. In this, he had to set his developing methodology against the prevailing one, that of Aristotle. Galileo's methodology included mathematics at its core, and this was vehemently opposed by church scholars because it was in great contrast to the Aristotelian method of inquiry, which had been turned dogmatic by scholastic scholars. The Aristotelian model of understanding was used by the learned people of his time, for example, by scholastic scholars in universities, such as universities of Pisa and Padua, in which Galileo was a faculty member, and was strongly supported by the Roman Catholic Church, which of course operated universities. Thus Galileo was strongly opposed and was persecuted, climaxing in 1633, when the Inquisition sentenced him to life imprisonment, but eventually allowed him to serve his sentence under house arrest in a villa near Florence, in which he spent the last 8 years of his life. In Aristotle's physics, there are 4 causes: material causes, formal causes, final causes, and efficient causes. Taking Michelangelo's David as an example, its material cause is marble. Its formal cause is its shape. Its final cause is its end or purpose. For example, fulfilling aesthetic goals and/or an educational statement about the biblical David's powers. And its efficient cause is that which initiated its process of change, namely Michelangelo. Aristotle says that in some cases 2, 3, or 4 types of causes may be the same. In Aristotle's scheme, changes or motions occur when matter acquires a form that it did not have before. He thought there was an ultimate cause for all motions, a final cause, which moves all else, as, for example, in an oak tree being the final cause and formal cause of an acorn's changes. Aristotle did not see the final cause or unmoved mover as divine, and in fact wrote that there are multiple final causes, but some Christians believed the final cause fit their idea of God, so it became wedded to Christian doctrine. More, Aristotle wrote that when motion or change occurs, the mover communicates the power of motion to the medium in which the change occurs, for example, air or water. That is, the first particle, let's say of air, moves both other air particles and the object being moved, and that objects move only while force is being continuously applied to them. This concept, of course, was contradicted by Isaac Newton, who was born a year after Galileo died, in his first law of motion. A body at rest tends to stay at rest, unless acted upon by an external force, and a body in motion tends to stay in motion, unless acted upon by an external force. The Newtonian idea also contradicts Aristotle's conclusion that motion is impossible in a void. Aristotle also taught that the Earth, a sphere, is the center of the universe, and that there are 2 different sets of physical laws, one pertaining here on Earth as we experience them, and the other in the heavens. The heavens, for example, the rest of the universe beyond the Earth, is perfect, in that it undergoes no changes, except in some cases changes in place. This was mortally challenged by Galileo's observation of sunspots seen through a telescope. Aristotelians also held that the stars are not made of the same 4 elements as those which make up the Earth, that is, earth, air, water, and fire, but are made of a 5th element called ether. The movement of the stars is explained by their being fixed to 49 or 55 invisible spheres, which are moved by an unmoved mover. The pursuit of scientific knowledge should not be subject to any authority, according to Galileo, but be it the authority of traditional wisdoms, of the occult, or the charismatic authority of any person or persons, or political, religious, philosophical authority. Significantly, Galileo also included the personal authority of a scientist or scientists, saying, "In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual." This last caution is often overlooked in our time. One reason for this is that contemporary science is based heavily on very advanced mathematics, and very few people indeed can understand such mathematics. Also, we imbue famous scientists with such awe that we forget they too have biases and are subject to error. For example, no less a scientific authority as Albert Einstein could ever in his life accept quantum physics because it violates the idea of a perfectly determined, perfectly orderly universe as he trusted it to be. Thus, the famous exchange between him and quantum physicist Niels Bohr. Einstein, God doesn't play dice with the universe. Bohr, who are we to tell God what to do? Galileo argued that observation be used in science and distinguish between objective and subjective observation. His argument here is very elementary, saying in the Assayer in 1621, tastes, colors, odors are nothing else than mere names, but hold their residence solely in the sensitive body, so that if an animal were removed, every such quality would be abolished and annihilated. More, Galileo insisted that observation should be made as objective as possible by being expressed in mathematics, and that all hypotheses drawn from observations be tested by experiments under as many controlled conditions as practically possible. And he championed the stances of doubt and skepticism toward all knowledge. No knowledge is final. In his dialogue concerning the two world systems in 1632, he said that human knowledge could at any time be only a finite part of an infinite whole of nature. In a very early writing on motion, which Galileo started writing in 1580 when he was 16 years old, but not published until after his death, he moved from purely philosophical and classificatory arguments, traditional at the time in physics, to mathematical treatment. And throughout his life, he made statements such as, "The book of nature is written in mathematical characters, without a knowledge of which men cannot understand it. And without mathematics, one wanders about in a dark labyrinth." In this, Galileo was revolutionary. As said by E.A. Burt, the birth of a new science, terrestrial dynamics, presented itself to Galileo as a simple and natural extension of the exact mathematical method to a field of somewhat more difficult mechanical relations. Others before him had asked why bodies fall. Galileo asks, how do they fall? With the expectation that the answer will be given in mathematical terms, emphasis in the original. In fact, Galileo's emphasis on mathematics has led some scholars to classify him as a Platonist. This is a view that ultimate reality consists of abstractions, forms to Plato, mathematics to Galileo, and all else in reality consists of imperfect representations of these forms. Of course, Galileo was a brilliant mathematician and became a faculty member in mathematics and chairman of mathematics at the University of Padua when he was 28 years old. In 1592, 3 years before, he had become a lecturer in mathematics at the University of Pisa after publishing a paper on the center of gravity in solids. In fact, by 1592, he had invented a geometrical calculus for the reduction of complex to simple figures and wrote an essay on continuous quantity. The latter was never published. In medieval times, astronomy was studied through only a single branch of mathematics, that is, geometry, but no more than that. Whereas Galileo conceived of the whole physical universe as a world of extension, figure, motion, and weight, and all immediate causality is lodged in quantitatively reducible motions of its atomic elements. In fact, Galileo's faith in the mathematical order of the universe was so great that it led some scholars to think that Galileo regarded mathematics alone to provide total confirmations of hypotheses, not only prior to experiments, but also independently of them. This opinion holds that it was fortunate that Galileo had to prove his theories to others, and so had resort to experiments. But this overlooks the fact that observation in some cases at least came first in Galileo's thinking. A case in point starts with the famous story of Galileo observing a ceiling lamp sway at the church in Vallombrosa near Florence, noting the regular rhythm of its oscillations, then forming a hypothesis, then translating the hypothesis into mathematics, then testing the mathematical hypotheses in actual experiments, and later applying this theory in pendulum clocks. It needs to be noted that when Galileo offered a challenge to Aristotle's cosmology in the dialogue, he argued in favor of the Copernican theory that the Earth revolves around the Sun and not vice versa. But nevertheless, in the beginning of that work, he made extensive use of Aristotelian arguments. Galileo also, for unknown reasons, continued to teach the geocentric model of the universe to his students. In addition to the heliocentric theory, also at issue in the dialogue was Galileo's argument in favor of his mechanistic theory to explain ocean's tides having to do with Earth moving. He found this akin to water sloshing in a pan held by someone who moves the pan. And in contention to Kepler's theory that tides are related to the moon, Galileo deemed Kepler's concept as being akin to occultism. Nevertheless, the fictitious Aristotelian character in Galileo's dialogue, who is used to mock Aristotelianism, is named Simplicio, who argued for the geocentric nature of the universe, and the other character is a stand-in for Galileo. The Church also opposed the heliocentric theory because it violated its reading of the Bible's book of Joshua, in which he made the sun stand still, and other biblical passages, for example, Chronicles 16:30, Psalm 96:10, Psalm 104:5, and Ecclesiastes 1:5. Against this, Galileo, in a letter of December 21st, 1613, insisted that the Bible not be used against science. Although Scripture can indeed not err, nevertheless some of its interpreters and expositors may sometimes err in various ways, one of which may be very serious and frequent, when they would base themselves always on the literal meanings of words. Hence, it appears that physical effects placed before our eyes by sensible experience, or concluded by necessary demonstrations, by reasoning, should not in any circumstances be called into doubt by passages in Scripture that verbally have a different semblance, since not everything in Scripture is linked to such severe obligations as is every physical effect. But on March 5th, 1616, the Church banned Galileo's writings and forbade him to hold or defend his doctrines in public. In 1604, Galileo had published his theory of acceleration, which also contradicted the geocentric view of the universe. Publication of the dialogue in 1632 incited the Church the next year to put Galileo on trial in Rome and over time convict him of heresy and place him under house arrest until he died 8 years later. It is very important to note that Galileo early on knew that there were criticisms of Aristotelianism by scholastic thinkers well before he challenged it. As Thomas S. Kuhn puts it, Galileo was not raised completely as an Aristotelian. On the contrary, he was trained to analyze motions in terms of the impetus theory, a late medieval paradigm which held that the continuing motion of a heavy body is due to internal power implanted in it by the projector that initiated its motions. Oresme, a French scholastic who was born in 1320 and died in 1382, sketched a similar analysis of the swing stone in what now appears as the first discussion of a pendulum. At least in Oresme's case, and almost certainly in Galileo's as well, it was a view made possible by the transition from the original Aristotelian to the scholastic paradigm for motion. Although Galileo's theory of falling bodies contradicted the Aristotelian theory that objects of different weights fall at different rates, contrary to common accounts, Galileo did not state a uniform gravitational force. The world had to wait for Isaac Newton to give this theory, and Newton was born 1 year after Galileo died. Galileo's role here in the development of modern physics is that of being a critical part of a greater process culminating in Newton. In fact, so too, Galileo's role in the development of modern scientific methodology of science was in his being a very important part of a process that began before him and was developed further after him. Was Galileo's anti-Aristotelianism a metaphysical position about the ultimate nature of reality, or merely a methodological one about inquiring after truth? Or was it an example of its own injunction against yielding to authority? After all, Galileo's development of scientific methodology is only implicit in his work and is incidental to his other ideas. As noted, Galileo, late in his life, in the Dialogue, 10 years before his death, made extensive use of Aristotelian arguments, but he was here arguing for a Copernican view, time convict or convict him of heresy and place him under house arrest until he died 8 years later. It is very important to note that Galileo early on knew that there were criticisms of all the teachings of Aristotle made by scholastic thinkers well before he challenged it. As Thomas S. Kuhn puts it, Galileo was not raised completely as an Aristotelian. On the contrary, he was trained to analyze motions in terms of the impetus theory, a late medieval paradigm which held that the continuing motion of a heavy body is due to internal power implanted in it by the projector that initiated its motions. Erasme, a French scholastic who was born in 1320 and died in 1382, sketched a similar analysis of the swing stone in what now appears as the first discussion of a pendulum. At least in Erasme's case, and almost certainly in Galileo's as well, it was a view made possible by the transition from original Aristotelian to scholastic paradigm for motion. Although Galileo's theory of falling bodies contradicted... I read this before, by the way. I'm sorry. Let's go on to the end. If Galileo's idea of mathematics was that it is only a methodological method and not a metaphysical concept about reality, then it is consistent with the dominant view today about the philosophical nature of mathematics. That is, that any and every mathematical system is a closed system proceeding logically from axioms chosen by mathematicians, and no mathematical system necessarily refers to reality. As was said when computer programs were but new in the general public, garbage in, garbage out. This view of the philosophical nature of mathematics, known as logical constructionism, was first developed by Bertrand Russell and Alfred North Whitehead in their landmark 3-volume work, Principia Mathematica, which reduced all of mathematics purely to logic. We cannot be sure whether Galileo viewed mathematics either as purely methodological schemes sometimes applied to reality, or did he indeed believe that mathematics is a metaphysical basis of reality, or if this matter ever came to his mind. Grazie per l'attenzione.